Good morning. Can you hear me?
Good morning, sir. Yes, we can.
Okay, so I think today's lecture wraps up um, the first part of course, um, and I'll return. This was basically medium design, which is uh, really most important for experimentalists. I mean, you will never see this in a theoretical paper. Theoretical papers simply assume that either this substrate or that substrate or both substrates are limiting, and they just move on with their models. But the experimentalist has to uh, sort of make sure that the experiments are done the right way. And um, this appears to be something that is widely ignored. So this is actually um, this paper is from 2009, but I should read out um, this same guy's paper from 2015. It's a sort of a passionate sort of request to do better experiments. I should also mention that actually I invited this guy some years ago to India, and he left completely disillusioned with the quality of work that was being put out over here, saying that. So anyway, coming back to what he says, um, this is the last comment um, which he kind of makes. His investigations of microbial behavior usually begins with observations, brilliant ideas or concepts, which then have to be distilled into practical experiments that can be performed and will yield results based upon which we can proceed. This process has to be underpinned with solid microbiological work in the lab and on the microbial physiology. This should include aspects of media and cell cultivation. This is the stuff that we're doing right now. This should include aspects of media and cell cultivation, preferably at an early stage of the experiment. If the craftsmanship we use is not sufficiently solid in any of the experimental setups, we will produce low quality data even though the intellectual idea might be excellent. Misleading concepts will disappear sooner or later, but incorrect data, once they have been published, are difficult to eliminate from the scientific literature because experiments are rarely repeated. So, I mean, this part is actually quite true. I mean, I think that a lot of difficulties in biology are because many of the experiments are poorly done, and then people theorize on top of it, and then on top of it, and they build a huge structure, superstructure on top of. So, if you see, for example, the literature preceding the Monod model, very very complicated explanations, simply because they didn't do careful measurements. At the moment the guy did careful measurements, it turns out most of the things are stoichiometrically coupled, and this complicated process can be represented by a single reaction for many, many cases. So here I mentioned exactly how design data to design a medium that gives you a single growth limiting uh, component. And I was going through this table. So this table is showing you a typical uh, what is called a minimal medium or a well-defined medium, as opposed to a complex medium that contains, you know, um, complicated components like yeast extract or peptone or meat broth or so on and so forth. This is a nice clean system, and what I was showing you is that for each of these components, you can calculate how much of it you need, provided you know how much maximum biomass concentration you expect to encounter, which is denoted X max in equation 3 here. You should also know how much of the element is required per unit biomass, and that, correct myself. So basically, y e comma x in his notation, which is how much element you have per unit of biomass, is nothing but 1 divided by y x slash e. So once you understand this, then x max divided by yxe in this formula 3 is nothing but x max multiplied by yex, which is basically how much element you require to make biomass of concentration x max, and then you multiply it by an excess factor Fe. So in this table, the Fe is chosen to be 1 for the component you want to be limiting, which in this case is carbon. So he has chosen the Fe to be equal to 1. And then applying that formula, he gets this E required to be 10. This is because X max is equal to 10. The growth yield, grams dry weight of biomass per gram of element is 1. And therefore, application of the formula gives you mass of element equal to 10. And since you have 10 grams of carbon, I think you have, can't remember now what was the calculation. I think I did it. I think you have 12 grams of carbon for 30 grams of glucose. Then from here to here, you basically go by converting how much mass of the element you want to how much of the medium you have to add. And then you just repeat this calculation for all the cases. So the second one would be, for example, the nitrogen source. In this case, you need 1 gram of carbon per gram dry weight. That's the YXE that is given over here. And then the excess factor you assume is 3, because this is not a limiting element. So the number is chosen bigger than 1. Given YXE, FE, and X max, calculate this number using equation 3. And once you know how much element you have, then you estimate how much of the compound will give you that much of the element. And then you proceed likewise. And as I told you last time, the choice of these excess factors is dictated by the degree of variability. The ones that wherever the YXE does not have much variability, you use a relatively small excess factor. Wherever the YXE is highly variable, it can vary plus minus, I don't know, 1000%, then you use an excess factor of 10 or 20. Is that part clear? I think this is all there is to it. So this is the theoretical construction of the medium. And once you have done this theoretical construction, then it is highly recommended that you check it experimentally. And the experimental check is done by using this graph, which you have already seen. This is using the formula X. What's going on? It doesn't allow me to write. Maybe I try. This is using the formula X max equals X0 plus Y Sx S0, where this quantity is negligibly small typically. So X max is equal to YSX S0. So basically, if you are actually limited by one component, then this formula holds. So essentially, if you take varying quantities of the initial substrate concentration and measure what is the maximum amount of biomass that is reached. So this would be an experiment where if this is time and this is x, let's say log of x, then The graph should go like this and then plateau out like that. This is your X max. So on the x-axis, you plot the initial concentration you took. On the y-axis, you plot the maximum biomass concentration reached. And that should give you a straight line passing through the origin. And this should continue theoretically up to a certain point, which for some reason this will not allow me to write on, somewhere here, up to this point. Beyond that, this graph theoretically shows that basically something else has become limiting. So for example, if this were done such that your medium was carbon limited, then progressively increasing the initial concentration of the carbon source would lead to a line increasing with a certain slope as shown here until you reach a particular threshold beyond which maybe carbon is not limiting, now nitrogen is limiting, which means that essentially the nitrogen gets over before the carbon gets over. And so once the nitrogen gets over, this graph is indicating that you will have no growth and therefore you'll have a flat line. So if I can add, this is the picture in the ideal case. This blue line is indicating the substrate concentration, and the red line is indicating the biomass concentration. This is the ideal case. By ideal case, I mean when the substrate is in fact limiting. The non-ideal case is when you run the experiment, or maybe I can just you run the experiment. This time, if you do the experiment, you may get something like this and then like that. And what you find is that your substrate concentration is still quite high when growth comes to an end. And this sort of indicates that basically something else got over, which you were not measuring. So this is S and this is X here. So if you get something like this, you know something is terribly wrong. Something else got over, and that is why. And when you are here, basically on this graph, you are basically on the flat line. If you add more glucose, it won't make any difference because it's the other substrate that is getting over, so you will get no more biomass. So that's the method he recommends for testing whether you got the right medium or not. If you got the right medium, you are basically in this linear regime. Double the initial concentration and your biomass will double. That's the region in which you want to operate. You want to operate somewhere, the linear regime. You don't want to operate in this regime. Is that part clear? I think that's all there is to it. This is medium design. Any questions, or can I sort of move on to the next topic?
So I guess before we move on, like I had a few doubts in the problems that you decided, if that is fine.
Not that I would do that it was assigned only 2 days ago, right? So I thought, why don't you guys work on it for a while and then.
So I just had a small doubt, like in one of the questions, like just a clarification. Like, so if you could open the batch reactor problem. Sorry.
I get to the screen somehow. Because I've saved all the things in files. Is there a way?
So I guess we open Teams from the applications, not the quick draw, not the quick access. That might.
Well, on my iPad, there seems to be only one way of opening it, right? Let me see. There is. Let me see if I can get it from my OneDrive. Yeah.
So in the third question,
In the
like we're
third.
asked to calculate this. Yes, sir.
Third question. Go ahead.
So we're asked to calculate the saturation constant Ks. Like
That, as I told you, is a complete cop out. I think that this question is taken from a book. I kind of disagree with it. The way they will do it is, well, you can, in principle, you can.
So what I was thinking is that we can draw like the graph of dx by dt versus x, and dx by dt we can estimate using some sort of regression from the data that we have. And there we can find like where mu m by 2 is coming. And then we can find the substrate concentration there.
Well, you can, but it's kind of hard, is what I'm telling you. I mean,
Exactly. So that was the problem.
So now the point is that let me see if I can. The point is that you will not allowing me to write on it. Not. Anyway, my point is that the region in which mu actually changes is so small that probably not get any worthwhile data out of it. Do you follow? I mean, there must be some region in which mu is actually changing with S, right?
Yes, sir.
That region is so small that it will not work out. So, in my opinion, this problem is not. I would ignore this problem. Now, the way people do it, if it would allow me to write, for some reason, it's not allowing me to write, is to fit it to the complete model. Understand what I'm saying? The complete model means not the approximate model we use, but I think I gave you the outline. You know, it comes down to dt on one side and some complicated function.
Yes, sir.
That integration, when you do it, gives you a very complicated function, and you can use that model to just do a complete fit over the entire range. But even that, you know, that's all fancy mathematics. But if this thing is to work, then there must be a sufficiently large range of data points over which this happens, meaning mu must be changing with S. But for the large majority of systems, you will find that mu abruptly switches from mu m to literally zero. It all happens within such a short period of time that you just don't have the data to fit it. So if you see that the given data kind of fit, so the place where it'll work is where the Ks values are large. Because if the Ks values are large, then mu starts to be smaller than mu m, at relatively large values of the substrate concentration. And when that happens, you may get a fairly wide region in which mu is gently declining with time. You get enough points. So try it out and see how it works out. Otherwise, I would skip this. Okay?
Fine. Thank you.
Any other questions? Okay, so actually there is one brief point that I want to make, which is I have to return to my so this is, I guess, lecture 9. Is this lecture 9 or lecture 8? Should be lecture 8, right?
Sir, it is lecture 9, I guess, because there are already 8 recordings in recording folder.
But we started on a. There are 2 lectures a week, and every week we have 2 lectures, so it has to be an even number. I thought.
So I guess the first one like isn't being considered because it was just an introduction. So it should be ideally be 10.
So this is September 10th. So one last thing I want to mention, which should be fairly obvious to you. This will be covered in more detail later on. So far we have covered mass balances for compounds, right? Like glucose, like carbon dioxide. Actually, we haven't considered for carbon dioxide, but we will shortly. Glucose, ethanol. You know. Now we can also consider mass balances for elements. By that I mean, for example, for carbon, typically these are taken for carbon, oxygen, hydrogen, and nitrogen. Simply because these are large enough to be measurable. So these are the ones that are considered. Now, and this mass balances for elements, this topic frequently is known as elemental balances. So what this is basically, intuitively, it's really obvious. So if you consider a reactor, the most general one for us being, let's say, the CSTR, where there's a feed in and a flow out, then so supposing we consider glucose, then we have a glucose in term, a glucose out term, and then a glucose consumption term, right? So let me just write it down to highlight the difference. So let's say we are talking about glucose, then this is the mass balance where this is the in term, this is the out flow rate out term, and this is the consumption term. If this were product, you would have a production term. Supposing I had to write such a balance for carbon, what would the balance become? So the mathematical part may seem a little tricky, but intuitively it's pretty obvious. if I wrote a balance for carbon going into a reactor and coming out of a reactor, what would the balance look like? Basically, this term will disappear. The reaction term disappeared. Yeah, if you have elemental balances. I mean, carbon can go in and carbon can go out, and carbon can also accumulate. But no, in a reaction, in any set of reactions that are taking place in a system, you cannot generate or consume carbon, right? Carbon is conserved. Are you following? I mean, is that making sense? I mean, any system of reactions, I mean, the elements are preserved, right? Unless you're doing radioactivity where, hydrogen goes to helium or something, fusion reactions. Unfortunately, in biochemical engineering, we don't deal with those reactions. In all our reactions, the elements are conserved. So, is that intuitively obvious? I mean, the mathematics I'll get to later on, but stated differently, if you, um, if you can describe growth by the reaction, y x s plus y x n ammonia plus y x O2 going to C H A times O times B n plus y xp of P plus y xc of CO2 plus y xw of H2O. Then, and let this be mu. Then, um, here is the first question: is why do you really care? Why do you need this? Who cares about elemental balances? Well, the reason is that um, you can measure, as I told you, many of these coefficients experimentally. For example, this one I even showed you how it is measured. It is simply measured in a chemostat by calculating the specific substrate uptake rate and dividing it by the growth rate, which is equal to D. So this is basically nothing but RS divided by D. That is what YXS is equal to. Or if you want to write it the other way as YSX, then it is D divided by RS. Likewise, if you could calculate, and you can, a certain degree of approximation, how much nitrogen is consumed simply by measuring how much nitrogen went in and how much nitrogen is going out of the reactor, and then dividing it by D, you could calculate YSN. You could also calculate this as RO over D. You can also calculate this as how much product you form divided by D, and this can be calculated as RCO2 divided by D. Okay, so all of these coefficients, except I put a question mark here, this you may not be very successful in measuring under certain conditions. Well, for example, if your medium is carbon limited, then by definition you have used 3 times excess nitrogen, right? It's in a huge excess. And if you put something in huge excess, then even if it is consumed, it declines by a relatively small amount. And if you're trying to measure, say, 100 minus 99, the measurements can be difficult. So For that reason, sometimes it can be hard to measure Rn, and water for sure you cannot measure. Cannot measure Rw. That's simply because your medium is essentially pure water. I mean, what's going in is essentially pure water with some salts thrown in. And that's like 55, I think 55 moles per liter or something like that. It's some humongously large number. And so whether water is consumed or produced is really hard to detect because the amount of water coming out will be essentially the same. So this quantity is hard to measure. Um, this quantity is, I should put it, this quantity is hard to measure, and this I'll put it there. Sometimes it is hard to measure, sometimes you can. Either way, the point is that if you know yxs, yxn, yxp, and yxc, all these obtained from measurement, then they immediately impose some constraints that your data has to satisfy. For example, it must be true, you can see right away, that the carbon balance says, I have not put this here, but supposing S was, you have to write the molecular structure here, but suppose S was in fact glucose, which is written as CH2O. You can write it, there is no harm. Then in that case, you can see that the carbon balance demands that YXS, which is the carbon in glucose, must be equal to 1, which is the carbon, the stoichiometric coefficient for carbon in biomass, plus YXP, supposing, this is, supposing P is glycerol, you have to specify what this is. So supposing this is CH3O, which is formula for glycerol, then you write YXP plus YXC. This relationship has to hold. If this relationship does not hold, so these are all measured quantities, right? This one, and this one are all measured quantities. If these measured quantities don't satisfy this relation, then you know something is wrong with your data. Your data has to satisfy this relationship. So for this reason, it is useful to do the elemental balances. It is to check if your data is correct or not. Now, I did this by taking a balance over carbon, but you could likewise take the balance for oxygen too. I mean, assuming that, so in this case, it would, the oxygen balance would read YXS plus 2 times YXO must be equal to B plus, this would be YXP, assuming that your product is glycerol and has a formula of CH3O, plus 2 times YXC plus YSW times, plus YSW. This is your oxygen balance. So far, so good. Can you follow what I'm saying?
Yes, sir.
Yes, sir.
So now you can already see, and this will be dealt with later on. Here, all I want you to understand is that elemental balances simply say rate of accumulation of carbon is equal to carbon in minus carbon out. There is no reaction term. How this happens mathematically, let me see if I can get back to it in a minute, but accept that at face value. Once you have that, if you're operating at steady state, then you know that carbon in has to be equal to carbon out, and that leads to a relationship of this kind. And a relationship of this kind then tells you that your data must satisfy certain constraints, such as the one for carbon, and the next one I put with a blue because there's already a problem. Can you use this balance? I just put down a balance equation for oxygen. Do you think you can use this balance?
So I think we can't because we do not know YXW.
That's right. You don't know this. And if I were to write another balance for hydrogen, do you think I could use that balance?
No, sir.
No,
Same
sir,
reason.
for the same reason.
For the same reason. So if you put hydrogen over here, you will encounter the same problem. And in the case of nitrogen, actually the balance is very, very simple, right? Because nitrogen appears only in ammonia and typically only in the biomass. I mean, you can see that the product, many of our products don't have nitrogen. So in that case, this balance in principle simply says YSN has to be equal to, the, I guess, C 3 times, is that right? YSN is equal to C. I think that's what it says. Um, so this is because nitrogen frequently behaves like all the other elements that we have considered, phosphorus, sulfur. These typically just they're taken up from the medium, and they have only one fate. They get into biomass. Unlike carbon, which you can see goes to all sorts of places. It goes into biomass. It goes into product. Likewise, oxygen goes into biomass. It goes into product. It goes into carbon dioxide. It goes into so nitrogen is particularly simple, and if you can find out this quantity, you can use this relationship, right? You know that YSN has to be equal to whatever the value of C is for biomass, and this, by the way, can be determined. The elemental composition is determined by using an elemental analyzer. This is also available. I think there is a unit in the department which one hopes will be available for your labs. You basically just shove your dry biomass, you put it into that instrument, it oxidizes everything, and then from measures the oxidized forms of these compounds. For instance, it'll look at how much water you have, how much carbon dioxide you have, how much of the nitrous oxide you have, and then spit out, basically tell you what is the elemental composition of your biomass. So coming back to it, 2 out of the 4 balances are essentially unusable. So you might now say, what do we do? So here, this is a trick that we will get to later on. I just want to mention it so that you can have a feel for it. What you do is you basically take a linear combination of these balances for C, O, H, and N in such a way that this YSW is eliminated. So this is like Gaussian elimination. Do you remember Gaussian elimination where you add equations to eliminate certain variables?
Yes, sir.
So the same trick is applied. And when you do that, it turns out that uh, the whole thing starts to resemble. You start. We'll do it when the time comes. I think I should stop here. So basically, you take linear combinations, and instead of working with, for instance, the balance for O or the balance for H, it will actually turn out that this YSW will be eliminated when you take the linear combination 4 times C minus 2 times O minus 1 times H minus 3 times N. Or is it plus 3 times N? I mean, basically, these are the valences of the elements. When you take the valences, that's when this YSW gets knocked out. So that particular quantity, which is a linear combination of the C, O, H, and N, that knocks out this unpleasant YSW, that is given the name degree of reduction. Uh, these things should actually have been covered in mass and energy balances, which is what I forget the number of the course. This is your first course.
So 133.
This is the infamous one taught by Sunil Nath. So I can pretty much be sure nothing has been taught. So anyway, this will be covered later on. That is the purpose. You do not use it. You do not use elemental balances uh, for, to my knowledge, any purposes other than. So I'm going to put it down. The technical term used is elemental balances. Elemental balances are used to check uh, data consistency. I mean, if you if you get if you get certain data, how do you know it is correct? I mean, are you just gonna accept whatever you got, or are you gonna see everything is checking out? So this is the reason why they have elemental balances, and it also turns out that if these balances are not obeyed, if they are not obeyed, if you, for instance, find that y-axis is not equal to 1 plus yxp plus yxc, then you can start to ask the question, what went wrong? For instance, do I have another product which I didn't pick up? Right? So basically, then your balance would be yxp1 plus yxp2. There is another product sitting out there which also has carbon, but you never picked it up. So it starts to reveal deficiencies in the work that you have done. Or, for example, there might be errors in your measurement. For example, this YXC, which is the coefficient that describes how much CO2 is consumed. This is typically measured by measuring how much CO2 goes in and out. And if there is an error in YXC, then basically the balance will not go through. And this error can arise simply because the flow meter that is measuring what is the flow rate of air going through the reactor, that flow rate is not correct. Or maybe the sensor that is picking up CO2 is not correct. So that's the way in which these are used. So we'll get back to this later on. So the last point I want to point out is to actually just to model things up a little bit more. I want to point out. Uh, so until now, this is just to indicate to you that this course is uh, barely scratching the surface. There are some very interesting problems that are there that are still being considered. So, um, what we have talked about, I'm again trying to show you. Take a look at the figure on the left. This is showing you. So on top you can see CNPSK. Each of these represents what happens when you do a shake flask experiment with that particular element being limiting. So on the left side is the case of carbon being limiting. And the first thing I want to point out is this is entirely in line with the model that we have developed. What is shown in X in blue is the concentration of glucose, which is limiting. And you can see that as soon as glucose gets over, that's when the biomass concentration X flattens out. This is the picture that we have had so far. If you look at the bottom, below that, in green, that is showing you the accumulation of acetic acid. And what this is showing is that basically during the first phase, when the cells are consuming glucose, you can see a little bit of acetic acid accumulating. This is the green arrow. And then once the glucose gets over, they basically eat up the stuff that they had excreted. So you can see that the acetic acid starts to drop. Now, the acetic acid part we never really cared about, but I think I have mentioned it earlier on. The more important thing is that this basic idea that when the growth limiting substrate ends or is finished, biomass level becomes constant. This is thrown out of the window when you do the same experiment with phosphate as the limiting. So take a look at this data. This is showing you look at the one labeled P. This is showing you the same experiment done when phosphate is limiting. And notice that when the phosphate ends, the biomass doesn't get flattened out. It just keeps on increasing. It just keeps on increasing. Does anybody have any thoughts on what's going on here? These are the kinds of problems that uh, that 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 these are not frequently mentioned in the undergrad books, but um, you can see that this is not a trivial Monod model type crank in something and crank it out kind of. It requires some creative thinking. What do you think is going on here? Does anybody want to take a shot at it? Why is it that upon exhaustion of phosphate, so this is clearly violating Monod model, right?
So the cells stop using ATP as the currency and use like ADP or AMP.
That's one possibility, but that's not the reason. It's a much easier reason. Actually, this is maybe let's do the previous case. Then let's see if you. So in the case of nitrogen limitation, right? You see that ammonia gets over and biomass increases, but very marginally. You can see a little bit of increase in X, right? This you should be able to explain. This we have already done. So basically, when the nitrogen gets over, if you take a look at the biomass, it's rising, but ever so slightly. There's a slight upward slope. Can somebody take a shot at that? This has already been discussed.
Due to an alternate form, like the biopolymer, which
That's right.
contributes.
So this is like basically the formation of the biopolymer. Now, but that's kind of small. In the case of phosphate, it seems to sort of keep on marching ahead, even though. So this is a linear scale. This is not a log scale. So it's increasing, but at a somewhat slower rate. And here on the right hand side is the data for phosphate limitation. Same story. Phosphate ended. Sorry, potassium ended, but the cells keep on growing. And if you take a look at sulfate, same story. Sulfate ends, but the cells keep on growing. When the element is not available, how the hell are the cells growing? So keep in mind, the element is not available. What you're tracking here is the availability of the element in the medium, outside. But it does not preclude the fact that this element might still be hanging around inside the cell in some stored form.
So they probably started recycling these.
That's what's going on here. So basically, they 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 stuff themselves while it's available, and then when it's over, then they redistribute it to the daughter cells to continue the growth. Are you with me so far? I mean, the reason why I'm pointing these out is that actually, in many cases, the way this course is taught, they ramble on in these books about the Monod model. After a while, you start thinking this is like Newton's laws. I mean, they've been around in their invariant form for 300 years. But actually, this area is sort of open to anybody with any creative thought. Really basic problems that are still waiting to be explored, and the book is a good indication of basically restricted it to the point where they reduced it to basically just elementary. So this is like really simple stuff, but you can already see that you need to modify the Monod model. Are you with me so far? I mean, all these cases will break down, right? The case of P, the case of S, and the case of K. All these three cases, they'll go to the dogs. I mean, if you apply Monod model, the Monod model will say X needs to flatten out, but your data will show that X is increasing. Now, actually, the moral of the story, I mean, at least according to this experimental guy who wrote the paper, is that many people don't even measure the substrate concentration while doing these experiments. So, for example, go back to the carbon. What people often do is they only measure X. So, I'm going back now to, I gave you this thing. I told you that if you want to determine whether something is limiting, you plot S0 over here and X max over here, and you will get a line like this followed by a horizontal part like that, and basically you want to operate in this region over here. This is what I told you a little while ago. Now, the important point I want to make is, how do you determine what is X max, right? How do you determine what is X max? Now, that is no problem when you're dealing with carbon limitation, right? You go and say, oh, you know what, my X max is where glucose got over. But if you come here, uh, if if you simply, and what people do is they never measure glucose. They simply measure the biomass level, and wherever it flattens out, they say that is my X max. But if you apply that principle to these cases, P, S, and K, if you basically say phosphate ends wherever X flattens out, you'll end up with total nonsense, because X is being, the X max is way higher than where the element ended. So in these cases, you should determine your X max precisely at the point where the phosphate ends. That's sort of the moral of the story, as far as this guy is concerned. So is that part clear? I think I'm not asking you to, on the minor, I might ask you to read a paper in which somebody is attempted to understand, say, growth on phosphate, uh, and I'll see if you can at least understand the paper. But for the time being, I just wanted to point out to you that road model kind of craps out. Um, the moment you move away from carbon. Is that part clear? Any questions?
Yes, sir.
Uh-huh.
Yes, yes.
Okay, so I think that pretty much covers everything here. Now, there are some 20-25 problems that I've given to you. In see, so I don't know how to do this. I really don't want to take an entire lecture to do problems. My suggestion to you is that you work these problems on your own, and then we can have one session where I will take questions. What would be a good time to do that?
Uh, so
Sorry,
like, so you want to take that before minor?
I think so.
So on a Saturday, I guess. Is that fine?
So today is 9th. We can do it this Saturday. That's the only Saturday we have, right? Am I correct, or do we have next Saturday too?
So we have next Saturday as well, but the minors
So,
are
but yeah, the minors are starting on the next Sunday. So
yeah.
Uh-huh. So, boy, that's it's too. I had other stuff lined up for this weekend. Can we
could
not?
take the 24th, the day after the minor ends?
No, that
Or
would be
or
that would be pointless, right? What's the point of doing the problems after the minor end? So let me
no,
just.
after the minor.
but the thing is, like your Viva is scheduled after the
your Viva is
original
scheduled. I'm talking about the minor schedule.
after the minor schedule.
Yeah.
I see. But I mean, I see this material. So 99% I'm going to give you, let's say 95% I'm going to give you papers to read. And if you have not understood this by solving problems, you will be clueless. Anybody thinking that they can just jump into a paper and start talking about it, it won't happen. So that's why I prefer that we do these problems. Let me think about it. Maybe I might even devote like a whole lecture. Is anybody going to try out the problems, or nobody's going to try out? There's no point.
So we did.
So
We have started trying the
Saturday,
problems.
maybe right then. Right, but I want to address all of them at one time, right? So I want you to be able to go through all of them. So since I've given you only the problems only, I think 3 days ago, I might as well wait for a week, right? You try them all out, collect your questions, and then we discuss them. Better that way than to just hold it this Saturday and then essentially give away solutions. I just want you to try, because I mean, once you try these problems, then you get a feel for the way people think. Then it'll be easier to read the papers that I send. Is that okay?
Yes, sir.
Okay, so
Yes.
I'm going to move on now to the next topic, which is um, uh, this is barring the questions that we the numerical problems we solve. So I'm going to move on to the next topic, which is um, um, momentum transfer. And see if I have. Oh, um, so this is the material that I'm covering is going to be follow very closely um, um, the book by Duran. So from now on, up until now, I have actually uh, really been doing my own stuff. But now I'll be following pretty closely the book by Duran. And I want to first of all mention that you guys have all done transport phenomena, right?
Yes.
I couldn't hear you.
Yes.
Is that yes? No.
Yes.
So, um, see, this doesn't have a. I want to go to chapter 8. So basically, I think it's chapter 8, but I'm going to request you to read a few topics in chapter 7. It'll be easier for you to understand if you. Gosh, is there no better way to scroll than. Um, So I want to go to chapter. Um, I think it's called momentum transfer, or this is the one, fluid flow. If you can just review this stuff, this is stuff you've already done. Um, maybe just go through it, review your. Um, it's pointless to repeat it. So you've done this stuff, right? I mean, viscosity. What is viscosity? What is a? Have you done this stuff? Have you done this stuff in fluid mechanics? Total silence. I mean, can somebody just speak up?
So can you, yeah, we have done this possible.
Um, I mean, this is the stress strain relationship for Newtonian fluids.
Yes, sir.
Um the velocity gradient plotted versus the stress. What is momentum transfer? Um,
Yes, sir, we have.
Have you also done different types of fluids, Newtonian
Yes, sir.
fluids and
Yes, sir, we have
non-Newtonian
done
fluids?
models. Yes, we have done.
Uh-huh. And you can skip viscosity measurements. This is not part of our lab, but let me get to the point where um, huh, this is stuff you haven't done probably. It is mentioned in Bird, Stewart, and Lightfoot, but you may not have done it. I would request you to read this part on your own. This is no see, this is not that. 7.9 turbulence 223. This you read on your own because the coming chapter, which is chapter 8 on mixing, will use the ideas that are stated here a lot. And the reason why I'm saying this is that your fluid mechanics courses and even your transport phenomena course, they basically spend all their time talking about laminar flow because that's what you can solve. But this chapter on mixing is about the real world, where you almost always operate in the turbulent regime, for which you really don't have a great deal of theory. It's a kind of it's a sort of semi-empirical. So read these. This is going to be used. They will, every page they'll throw in this word about eddies. Have you done this stuff in fluid mechanics? I seriously doubt. Does this thing resonate? Eddies in turbulent flow?
No, sir, not indeed.
So this is by and large it's descriptive, and just read turbulence. That's it. Um, if you have trouble, you let me know. Then I will cover it. But for the most part, um, the most important part is actually this part here. Um, up to, I think you don't have to measure turbulence. You don't have to do turbulence measurement. You don't have to do computational fluid dynamics. So This is also you can skip. This also you can skip. So I would just cover the section on turbulence up to no need to look at the experimental techniques up to this point.
Yes.
This is used quite a bit later on. It's for the most part, I would say, semi-empirical. Just read it, and then we will start basically with the straight away with chapter 8. So we will start with
So we will start with chapter 8 on Monday.
yeah.
Okay.
And I think I have already covered this. These, in a typical semester, we have already shown the students what a bioreactor is, because the lab runs in parallel with the course. But this time around, we don't have it. So I had shown you this picture, but you can also take a look at the beginning of, just review it, the beginning of the chapter, just see the diagrams and understand what is an impeller, what is a sparger, what is a shaft, because this chapter on fluid mechanics is all about designing how do you choose impellers, how do you choose what power should you give to your stirrer in order to make sure that the liquid is well mixed, the gas is fully dispersed, the solids, by which I mean the cells, are not settling at the bottom, they are also fully dispersed. So this is basically a chapter with quite a bit of empirical stuff, giving you the formulas you need to make sure that you're operating your reactor in such a way that everything is properly mixed, solids, liquid, and gas. And much of this hinges upon properties of the reactor. What is the baffle size, what is the impeller size, what is the nature of the sparger. Just review this part. I mean, that's really not hard. I mean, just take a look at a few pictures and you're done. Fair enough? So we'll start next time.
Yes.
Okay. All right. Okay. Thank you. So I'll see you on Monday.
Thank you.
Thank you, sir.
Sir.